Okay. So I'm going to go ahead and get started here with kind of picking up a little bit from last time. So last time I talked about the first order system. And we said in general we have the basic first order system. I have an input, an output, right over there's a transfer, a differential equation relationship between those two in the time domain. And then ultimately I can make a transfer function relationship which has a single pole. All right, so remember, poles are the roots of the denominator. Zeros are the roots of the numerator. So in this case, I've got one particular pole. That pole is at the root of the denominator, negative 1 over t. Okay, so we're going to explore this guy a little bit more today. All right, now just to wrap up a little bit, I started talking about performance specifications last time, and those are in the notes that I'm posting up to go with that lecture. Okay, basically what I talked about was time domain specifications. Because in general what we're worried about is getting some sort of set of performance specifications when we're designing a system. So when I'm going into a control system, typically what I'm trying to do is maybe make the system respond faster to a particular input and make it have zero error for a particular input. So I just wanted to explore those concepts again real quick since I was sort of running out of time at the end of last lecture. So in your notes and in class we talked about this. What you're looking at right here is essentially the impulse response, which we said the impulse response basically is the natural response. The impulse response is basically where I'm looking at if I excite the input very quickly with a short pulse, and I look only at what the impact of the system is, okay? So essentially what I see right here is the impulse response, the natural response we call it, all right? And I see how it decays, all right, if I've got a single order system. Relatively easy to figure out what this is, but I can define a couple of things, right? First of all, the time constant tau, which in this case is written t. I'll write it in your stuff always as tau. Okay, but in this figure it's written as capital T. If I look at this, essentially what I see is that tau, by definition, at time t equal 1 over tau, or in this case, as it's drawn here, t equal to capital T, essentially that's the point at which the initial value, all right, that the output is dropped to 37% of its initial value. At this time, tau, at the time constant, my output is dropped to 37% of its initial value. Okay? And what we see essentially is that by 4t out here, by 4 tau, 4 times the time constant, the output is more or less become very, very small by that point. Okay? In fact, as it says in your notes, right, there's a couple of key quantities that I sort of begin to refer to in any of these sorts of things. And I'm going to go over a couple of those here right now. But if I want to look for specific time domain specifications, there's a couple of things that I might do. So let's look at another type of input, the step response. So if I put a unit step into my system, this would be my step response for that canonical first order system. So again, what I can see is that in a time constant tau, one time constant, my output essentially reaches 63% of the final value, okay? And that time constant clearly defines how long it takes to reach the final value. And that's why I've written this sort of dimensionlessly down here on the time axis, because what you see is this is one time constant, 2, 3, 4. I wanted to kind of express the power that the time constant has. All right? So a couple of things that I can look at in looking at this picture. One thing is clear is that what we call the speed of response is dictated by this time constant. Okay? The faster the time constant, the faster I reach the final value. Now in this dimensionless graph, okay, what I see is the time constant clearly controls how fast I get up here. If my time constant is faster, then I reach the final value faster. All right, my time constant is basically if it's smaller, I reach the final value quicker. If I have a big time constant, I reach the final value slower. Okay? But in general, in terms of the time constant, I see a couple of things, right? One, quantity, so speed of response. Clearly the speed of response is controlled by the time constant. But I also talk about settling times, what I call 5% settling time, 2% settling time. So something like 5% settling time is what I call how long does it take for the output to reach 5% of its final value. So if I were to say, how long does it take until this output here, this signal, gets to 95% of its final value? So in other words, 0.95. Well, what we find out is if you plug into this equation, you see that the output C of t equals 0.95 at about 3 time constants. All right. So to settle to within 2% of its final value, or about 0.98, okay, so put in how long does it take to get to 0.98 and solve for t, what I'd find is that's at about 4 time constants. So very often we say that by 4 to 5 time constants, any of this transient behavior is dead, and what we're looking at is just the steady state response of the system. In other words, the circuit or the system itself has sort of fought off that change. It stopped opposing the change and effectively follows the input. Now, we've looked at 2 types of inputs, right? Unit step is a very common one. Basically, we said if I had like my DC motor and I applied a constant DC voltage to that motor, right, that's like a unit step. Now, in a lot of cases, let's say for instance I was building like a radar tracking system or something, I might have in that case a unit ramp input. Okay? So let's say I had a unit ramp input. So in this case my input R of t is equal to t. I call it unit ramp because it's got a slope of 1. All right? And I see my ramp is basically just ramping up, towards infinity. So this is an unbounded output. Okay, so obviously in this case with an unbounded output, unbounded input, so I will get an unbounded output. So C of t here is my output in this case. Now you should know if I put a unit ramp in, since this is an LTI system, we're talking about LTI systems, linear time invariant systems, that if I put a unit ramp into the system, then the output C of t should be the integral of the step response, right? We know that for LTI systems, if I apply a unit step, I'll get this response. And we know that with an LTI system, if I apply the integral of the unit step, meaning the unit ramp, then what my output will be is the integral of this response, okay? And the integral of that response is shown right here. So what am I looking at? Essentially what I'm looking at is, as we said, all of these systems, anytime I apply an input, okay, initially the system opposes that change. Okay, so initially what we see is opposition to the change. But eventually that opposition decays. So again, by about 4 time constants, right, we say we reached 2% of the final value. In this case, the final value is a ramp, right? What's supposed to happen is if I put a ramp into the system, eventually the steady state response is to follow that ramp. Okay, so eventually initially what I have is an exponential plus a ramp, and eventually the exponential is dead and I'm just basically ramping up at my output. Now the important thing I wanted to kind of point out right here is this idea right here, that there is a steady state error. If I look at this, the output is always a time constant below. The actual value is a time constant off from what the input is. In other words, if my time constant was 0.01 seconds or something like that, this output would be 0.01 volts below this input. That's steady state error, okay? And I can, maybe I should write out that equation so you can kind of see it. If I looked at what this equation was, all right, what I would see is that C of t equals t minus capital T plus t e to the negative t over capital T, like that. right? So if I were to look at this guy in steady state, clearly this term goes away. R of t is equal to little t. C of t is going to be little t minus capital T. So essentially what you're seeing is that there is always, in steady state, once this exponential is dead, there's always a difference between the output and the input. That is called a steady state error. Now, in a system where I have this as my input, okay, this ramp as my input, and again, or maybe a radar tracking system where I'm moving a radar dish or something, that might be the type of input I have. If this difference between the input and the output is not desirable, if that's a problem, I have to find a way in my control system to be able to get rid of that. So one thing we might talk about as another measure, performance measure, might be, okay, how quickly do we get rid of the transient response? Okay, and we can specify that in a couple of different ways. But the other thing might be to say, how much error do we have in steady state? Okay, so that might be another performance measure that we talk about. All right, now, where I ended up last time, and really where I want to finish up here today, is to talk about how we will look at the transfer function and try to relate a lot of these time domain performance specifications to what's going on in the time domain. Okay? So let me look at an example here. All right, so let's say I have this transfer function right here, 1 over s plus 4. Now clearly this guy has a pole at s equal minus 4. Okay? This one has a pole and a 0. I want to kind of explore this because what I say in general is, remember, when I look at the S-plane, and let me bring back up the S-plane here. All right. When I look at the S-plane right here, what I see, very importantly, is that S is a complex valued function. Okay, so S we write like this. The variable S has a real part and an imaginary part. So in this case, if I look right here, we see that my pole is at negative 1 over t, right? That's the value that makes the denominator equal to 0. And I always specify that with an x. All right? So that's a purely real pole. Okay? Purely real pole because, right, the value of s that makes this numerator, or this denominator equal to 0 is negative 1 over t. That time constant is always a real number in a first order system. Okay? But in general, what I see is that the transfer function g of s can have values at both on the real axis, okay, as well as on the imaginary axis. So essentially, the transfer function is a value, it's basically a function of a complex variable. Sigma plus j omega is the way that we'll write that. Okay? So let's look at what that means. Okay? So essentially what that means is, let's say I look at something like this. Well, that means that g of s is 1 over s plus 4. Or if I look at this, that means that it is sigma plus j omega plus 4. All right. So if I want to plot that, right, and I wanted to understand what this multi-valued function looks like, I could say, remember, since this is a complex function, I need to look at, I can't just say plot it, right? I have to look at magnitudes and angles. So I can say that this guy is, let me do it this way. I can write this guy as, if I want to write the magnitude of that, I can say like this, right? Since that's this should be a good review. Alright, I can say that this is sigma plus 4 squared plus omega squared. Okay? That's the part that we effectively look at. All right? Now, what does that look like? If I were to plot this, so basically to plot this on the S-plane, I'd have to look at the value of this guy for a bunch of different sigmas and a bunch of different omegas. Okay? So what I would get is something like this. Okay? So I did this in particular for that function, S1 over S plus 4. All right, now if I look at this, here's what I would initially see. All right, here's the magnitude of g of s. So I drew it three-dimensionally, right? Versus sigma and j omega. And what I see is that right here at the point where s equals minus 4, this guy is basically all low, but at s equals minus 4, he jumps up towards a really high value, essentially towards infinity, right? Because what do I have at that point? I have 1 over 0. 1 over 0 should be infinite. And that's basically what I see right here. And I see, if I rotate this guy around, I'm going to flip it like that. That's good enough, okay? What I see is that where the real part equals negative 4, boom, he just shoots off towards infinity, okay? So it's hard to see in some real detail. If I look at this guy, let me see. I'd have to really zoom in to see what's going on, but I see that the value sort of shoots off to infinity right there. That's why we try to draw that on that pole 0 diagram, like I showed right here. We draw a pole as an x, okay, because it shows that at that point, all right, the function is shooting off towards infinity, as we see right here, okay? Now, what about if I had something like this? Well, here I've got a 0 at negative 5 and a pole at negative 2. All right, so let's look at that guy. All right, so again, not sure why it's, there we go. Let me see. Let me force this guy. All of a sudden he doesn't want to show me the same thing he was showing me before. Oh, there we go. Okay, good. All right. So this function again, so a 0 at negative 5, a pole at negative 2. What do I see? Again, if I look at the full view of it, basically what I see is this guy at negative 2 at the pole location. So at the real equal negative 2, I see it shooting off towards infinity. Okay? Hard to tell if there's anything else going on right there. But if I zoom in, so notice the difference between, so this graph right here, I'm showing you the whole thing, and this z-axis, the magnitude axis, shoots off to infinity. Here I am zoomed in. Basically, I'm just showing you from 0 to 20. And what I can see is that there's some action down here. Right? I see that, yeah, at negative 2, I'm shooting off towards infinity. But here at negative 5, I see that the function is actually reaching 0. I zoom in on that a little bit, sort of spin it. You can see right there, I can see, let me spin it back. I can see that little divot in the function at negative 5. Try to rotate it up so you can see it. you can see how he dives down to hit 0 right at that point. So essentially, this is what when we look at the magnitude of the transfer function, this is really what it is. Now, very often what we want to do is we want to look specifically at the frequency response. In other words, if I look at either of these two transfer functions, let's say I'll focus in on this guy for a second. What we often do is I say for that transfer function, I will say, let's assume we have a sinusoidal input. So let's assume I have something of the form V cosine omega t. Okay? Well, when I say that, essentially what I'm assuming is that I have a particular input to the system. Okay? When I'm looking at the frequency response, I'm assuming I have a sinusoidal input, which means that ultimately I am talking about inputs of the form e to the j omega t plus e to the minus j omega t. Okay? And again, I guess I should, just to be careful, say that this is all divided by 2. Okay? So if I apply exponential inputs with that particular frequency, e to the j omega t, what you should know is that with e to the j omega t as my input, if I try to say C of s equals g of s r of s, if I have this, all right, what you should know is that this is equal to j omega times e j omega t, like that. All right? In other words, I'm able to plop in, I say that if I'm having an input that looks like that, I basically say I want to know the output where s equals j omega. So that means that I take this transfer function up here and get rid of the real part. Okay? That's what you guys have seen before, and that effectively is what the Bode plot is. I am assuming that my input is a complex exponential function, okay, like this, meaning that I'm assuming that it's a trigonometric function. It's a cosine or a sine. All right, and given that, when we assume that type of input, that g of s simplifies to this, and I begin to talk about what I call the frequency response or the Bode plot. And very often I can relate this frequency response or Bode plot to a number of useful time domain parameters, which we're going to look at a lot more carefully here as we go. All right?